Okay, here we are with the modelling section then, part B of this paper. Let's have a read through and get cracking on it. So it says, advises you're supposed to spend 45 minutes on this part, so same as the first section. We got this information, volume of a cylinder, which is all information that we know, and volume of a sphere. So fish ponds, hemispherical or cylindrical. That's a hemispherical one, nice diagram, and a cylindrical one. Quite interesting here that it's saying that the D value here, interesting they use D, which is a radius, is the same as the height of this. And that we'll come to that later. But first of all, a hemispherical pond, so we're looking at this one, has a radius of r when r equals 3. We need to show that it's 18. So plug in r is 3 into our formula. Well, our formula is 4/3 pi r cubed, pi times 3 cubed, and we want half of that, so I'm just going to multiply by a half at the start, which actually cancels with 2 of those 4, so we've got 2/3 pi times 3 cubed. Well, actually 3 cubed divided by 3 leaves us with 3 squared, which is going to be 9 pi times 2, so 2 times 9 pi, that equals 18 pi. There we are. So let's move on to the second part. B, a cylindrical pond now. Cylinder has a radius of d and a depth of d, so that's what we were looking at earlier, that this radius is the same as the depth. Show that the volume of a pond is pi times d. Okay, so we're not given a value for d this time, so we just need to put it into our formula. So it's pi r squared. R obviously is now d. Pi d squared times d, which is pi times d cubed. That's quite nice. The radius of and depth of the cylinder in part B is the same as the radius of the hemispherical pond in part A. Show that the cylindrical pond holds more than that with the hemispherical. Okay. First thing I'm going to do here is just make sure I label it. I haven't got a great deal of space, but I'm just going to write in here where I'm dealing with hemisphere. So our hemisphere was 18 pi. We've already worked that out. Oh, forgot my 18. 18 pi. Now my cylinder, instead of d cubed, it's going to be now 3, because this d value, if we look at this at the top, d value is the same as this r value. So I'm going to use a d value of 3, so it's going to be simply pi times 3 cubed, which is 27 pi. So what does it say? Show that the cylinder holds more. So therefore cylinder holds more. Okay, part D. A hemispherical pond of radius r has the same volume as the cylindrical pond of radius and depth d. So now what we need to do is we need to set them equal to one another because they've got the same volume. That's the key bit of information here. So we need, well, we know this, pi times d cubed needs to be equal to, it's pi, well, it's half of 4/3, I'll write it out again, half of 4/3 pi r cubed. And again, we can simplify these fractions. That 2 goes with 2 of those, and so we have, tell you what I'll do, in this first move I'm going to cancel my pi as well. I'm going to divide through by pi on both sides, just to tidy things up a touch. So d cubed equals 2/3 pi r cubed. Now it says we need to, well, we can see here we need to make d the subject, so let's just look at that. So I need to cube root both sides, so d equals the cube root of all of this. Oh no, my pi's gone. my pi went. That's fine. My pi was never there, I cancelled it. My pi is not here now. Tell you what, it looks like it never happened. And so I can cube root both of these things individually. Leaves me with a d being equal to the cube root of 2/3 times r, which is exactly what we were asked to find. So there we are. Okay, let's move on. Theo wants to work out how many fish he can put into a pond. A fish needs 5 litres of water for every 0.1 centimetres of its length. Average length of 15 fish is 18. Find the number of cubic metres of water needed for these fish. Okay, there's a few challenges, a few layers here to this question. So the first thing we need to think about is how much is the length of his fish, I suppose, in total. It's probably how I would label it. So grab my pen. So total length is going to be, well, 15 times 18, basically undoing that average, and that comes out with 270. So that's 270 centimetres, my total length of the fish. We know we need 5 litres for every 0.1, so we need to work out how many 0.1s that is. So we need to multiply by 10. So 270 times 10 gives me 2,700. Effectively that's, and if I'm going to label this, just for my mind, that's 0.1 centimetres. Yeah? There's 2,700, 0.1 centimetres in the total length of the fish. We know we need 5 litres for every one of those, so we need to do 5 times my 2,700. And that's going to come out as 13,500 litres. Now, that's all good and well, but we've got another challenge here in that we need to find the number of cubic metres. We found the number of litres, because this is litres here, so we're keeping consistent with our units, but we now need to add in that extra layer, that extra complexity to the question, I suppose, of converting this now from litres to cubic metres. Now, this is the bit that requires knowledge. You just got to know this, which is a shame if this is the stumbling point for you, but we need to know that 1,000 litres, where are we, black, 1,000 litres is equal to 1 cubic metre. Which means to convert I need to divide by 1,000, so therefore we need 13.5 metres cubed. Okay, quite a lot of, as I say, lots of layers in that question there, which is reflected in the mark scheme. There's 3 marks on offer for this part A of this. Everything previous to this has just been worth 1 single mark. So let's have a look at part B and see how we're adding to this. There are F fish in the pond with an average length of L. Find a model for the number of cubic metres of water W needed. Right, so this is going through the whole process that we've done. Let's just go through what we did previously. So we did F fish. So to my F, what did I do? To my F is 15. Average length L, well, I multiplied them together. So let's write that out. FL. Then what did I do? I then multiplied by 10 because I needed it into 0.1. So let's do that. Times by 10. Then after that, I times by another 5. Times by 5. And after that, I had to divide by 1,000. Divide by 1,000. And we need to tidy this up. 5 divided by 100 is 0.05, so we want 0.05 lots of FL. And we can check that from the example that we did previously. Check that what we're saying in part B is consistent with part A, and if we do 0.05 multiplied by 15 times 18, we should get 13.5, and when I put it into my calculator I do. So I've got a bit of confidence in my answer here. Let's put this in 0.05 FL. Next, we're going from a general case to this more specific case of Theo's pond, which has a volume of 20 meters cubed. I need to use my model to find the maximum number of fish of average length 24 that can be put into this pond. So, I guess at this point I'm thinking about water, and I'm just thinking I probably missed something on the previous question. So that should equal W, or W equals this. So now we need to, and it's quite nice sometimes that you can work that way, that the next layer of question makes you think, oh, did I actually finish the previous one? Make sure that you tidy it up. So the water that we've got is 20, and that needs to equal 0.05. Now I need to work out what it is. It probably doesn't make a great deal of difference, but the length is L, so it's going to be 0.005 times 24 times F. So I need to do 20 divided by 0.05 lots of 24, and when I put that into my calculator I get F as being equal to 16.6 recurring, which implies therefore that I can only have 16 fish, right? I can't have the 17th, there's not enough space for the 17th one in there. You can't round up in this context, so it's 16 fish. Okay, moving on. Theo's pond is hemispherical. Find its radius. Well, we know our formula for that. After the hemisphere was actually 2/3, wasn't it? After I cancelled with the half and the 4/3, pi r cubed, and that has to equal 20. Solving that, straightforward process, is 2.12. And if Theo's pond is a cylinder, and the radius and depth are the same in the context that we've got, so that was just pi r cubed, wasn't it? That would equal 20, so that's my radius r. So I need to do the cube root of 20 over pi, which comes out at 1.85. Okay, that's quite good. We've making progress through this. I think if I'm going to reflect on that page, the part A really did open up everything else. From there, it was just following the same process or applying the formulae that I've already used. Question 3 then. Theo decides to have a cylindrical pond. The radius r meters does not have to be the same as the depth d. For a pond with volume 20, find a model. Okay, so what's he going to do then? He's going to have 20 meters cubed still, so it has to be a volume of 20. So this is going to be 20, and that has to equal pi r squared times by the depth d. Yeah, that's just how a cylinder's put together. Now we need to just make sure that we're writing this and how it's asked. So a model for the depth d. So the key bit of information is how that's phrased. A model for the depth, which means we want to make d the subject of this, which means I need to divide through by pi r squared. So d equals 20 over pi r squared. Okay, next it's asking me to sketch this graph. So the process that I've gone through is I've put this into my calculator. In the calculator I've just changed my r for an x. Kind of makes sense because r is on the x-axis. So it should look exactly the same. And I've just put in 20 over pi x squared, exactly what we've had on the part A. and using my control table I'm able to see these values. So 1 has a point of 6.3, so up near that 7. I can see the general shape, and 5, it comes down quite quickly, and 5 has a point of 0.25, so it's going to be something like this, and I can see the shape from my calculator. Oh, that looks good. Lovely, beautiful curve. Okay, let's have a look then. So what practical problem is there now when the radius is less than 1 meter? So where am I looking at here? Where it's less than 1 meter. So my y values are less than 1 meter. That happens at a depth of about, the first whole number value I get looking at the table on the GDC is depth of 3 meters. I mean, a radius less than 1 meter, it's getting pretty deep already. So the practical problem is going to be that it's going to be too deep to dig. Okay, the next question, find the radius of the pond when the depth is 1 meter. So I need this depth to be 1. So this is exactly what I've done in my GDC. I put in a second function, y equals 1, and looked for the intersection using analyze graph intersection, and it gives me a point of 2.521. So on my graph, my GDC looks like this, and it's labeling this point at 2.521. So my answer here is 2.52. Okay, the water level must be 30 centimeters below the top of the sides of the pond. Modify your model in question 3. Okay, what does that mean? Well, the water, the volume 20, in my mind, would have to be 20, would have to be equal to pi r squared. That's not changed. Now the depth has got to be d take away 0.3. Obviously we've been dealing in meters because everything's in meters cubed, and now we're dealing in centimeters, so I've incorporated that by writing 30 centimeters as 0.3 meters, and here we are. This is what we've got. So my function now looks like 20 over pi r squared plus 0.3. That now is d. So that's going to be my new function. That's the answer. How does this affect my graph? Well, from the original to this one, I've basically done my f of x, whatever that was. In terms of graph transformation, I've just added 0.3. So we know from our graph transformations that that is a shift, or I shouldn't, let's use the proper word, shall we? It's been translated up 0.3. And I think that's us. There we are. We're all done.